Why are series and shunt impedances crucial in transmission lines? Imagine trying to send electricity across hundreds of miles without losing power or causing issues. That's where series and shunt impedances come into play, acting like the traffic rules for electrical currents. When electricity travels through a transmission line, it faces resistance and other effects that can change how much power gets through and how stable the voltage remains. These effects are described by series and shunt impedances, and understanding them helps engineers keep the power flowing smoothly. Series impedance mainly includes the resistance and inductance of the line. Resistance is like the friction that slows down the current, causing some energy to turn into heat and be lost. Inductance, on the other hand, is related to the magnetic field created by the current flowing through the wire. It causes reactive voltage drops, which don't waste power but can affect the voltage levels along the line. Together, resistance and inductance from the series impedance, which influences how much voltage drops and how efficiently power is transmitted over long distances. Shunt impedance, often called shunt admittance, involves the capacitance and conductance between the conductors and ground. Capacitance is created because the conductors act like the plates of a capacitor, storing electric charge. This causes charging currents that can raise the voltage at certain points, especially when the line is lightly loaded. Conductance, which is usually very small in overhead lines, accounts for leakage currents through insulation or corona discharge. These shunt effects impact voltage stability and reactive power flow, which are important for maintaining proper voltage levels in the system. Knowing these impedances helps engineers design better transmission systems. For example, they can predict how voltage will change along the line and decide where to add devices like capacitors or reactors to keep everything stable. If the series impedance is too high, it can cause excessive voltage drops and power losses, reducing efficiency. If the shunt capacitance is too high, it can cause voltage to rise too much, risking equipment damage. In practical terms, models of transmission lines include the series impedance to representing the resistance and inductance, and the shunt admittance to account for capacitance and leakage. These models are used in load flow studies, fault analysis, and reactive power planning. They help ensure the power reaches homes and businesses reliably and safely. So, series and shunt impedances are the backbone of understanding how electricity moves through transmission lines. They help engineers keep the system balanced, efficient, and ready to handle the demands of modern power systems and renewable energy sources. Without them, managing long-distance power transfer would be much more complicated and less reliable.